I guess we can start here. So this is like this is our processor. It's the brain, the computing chip on the board. And that essentially is going to be our interface to all the sensors, interface off the board, and how we're going to take the measurements from the sensor and process it into something useful. So this is the brains here, and then everything else is kind of just peripheral. So we have our a USB plug here. This is something that you don't really have to worry about. This is a CAN transceiver. It's if you want to use the CAN bus, this is sort of just like out of my interest, but don't worry too much about that. We probably won't use it really. CAN is just like another protocol. There's sort of like, when you get into electronics design, it's kind of a little bit of a steep learning curve when you want to learn about all the different protocols, which is basically how you talk to a sensor, how you talk to other chips, how you communicate off board. It's kind of akin to HTML, if you want to talk about it at the level of like the internet, TCP, IP. Here, the way that electronics talk to each other is primarily with, at kind of like the hobbyist level, 4 main protocols. One is I2C, and then we have SPI and UART, which is just like your serial communication. They all have like their pros and cons. SPI is the fastest, but it needs more pins, for example, and then I2C is slower, but you need less pins, less wires to connect everything. And then CAN is another one, which is kind of like automotive grade. So it's very robust. You can communicate over like really long distances with it. Which, it might come in handy if you want to have a lot of different cool things on the rocket. For example, if you want to like chuck a reaction wheel on there, you don't have to design specific, another like specific protocol to communicate with it. If you just have a CAN line, a CAN bus, you can just hook that up to the reaction wheel or like your servos or your motor and control it all like that. But yeah, don't worry about that too much. We have our barometer. So this is detecting humidity. It's like an absolute measurement for how high we're at, the height of the rocket. And so we're going to use this information alongside our accelerometer and our gyroscope and our magnetometer, bring all of those measurements together, probably with like a Kalman filter or something, and that's going to provide our pose for the rocket. So it'll let us know how high we go, what forces are acting on it, and our orientation. And obviously orientation is very important because you want your rocket to go up. If like your rocket crashes and you realize that it just went sideways halfway through the flight, if you can get the logs back, you can figure that out. But it's all sort of like data logging. Here we have our flash chip. This is just to store data intermittently while the rocket is flying. I covered it last week, but SD cards are not very robust in rockets because they're a mechanical connection. You can corrupt the SD card just because it's vibrating so much. So the plan is to log everything to a flash chip first, and then once it's the rocket's landed back safe, it's going to write everything from the flash to the SD card. We have all of that. And then this little circuit here is our Pyro Channels. So this is how we're going to actuate like our parachutes or whatever staging that you want. You don't have to worry about this too much right now. Essentially, all this is, I actually have to do some changes with this because I don't think this is going to work with nichrome wire. Essentially, all this is doing is pulling a bunch of current from the battery. And when the current goes through the nichrome wire, it heats up and you can cut a rubber band or ignite some like black powder or something to blow the nose cone off. And it's controlled by this transistor here. So the chip, if we pull one of the GPIO or one of the IO pins high, we can turn on this transistor and that's going to allow the current to flow. But I need to redesign this because I don't think it's going to provide enough power. But for now, to get the concepts across, it's totally fine. Over here, there's a slight change from last week. This is our 3.3 volt regulator. So I want it to be powered from USB. I want to do all of like the debugging and the programming over USB. And so when we connect to USB and then we connect a battery, for example, if the battery is like at 8.4 volts, without any kind of like protection, it's not going to be like happy days. Something will probably break, or the battery might short, or you might blow up the power supply on your or the USB port on your computer. So this is what this little transistor here is doing. Essentially, if we are ideally, you just don't connect the battery and the USB at the same time. But everyone, I would do that. So if we just have our battery here, this is at about 8.4 volts because we're using a 2S LiPo battery. That is normally going to be fed in here with this NFET. If the 5 volt USB isn't plugged in, this is going to be open. So it's a PFET, P channel MOSFET, which basically means when you pull the gate high, so this is like your control signal here. If this is high, it turns off. And if this is low, it turns on. So it's like negative logic. If you have an N channel MOSFET, it's normally open. And then when you put a signal here, it'll close the switch. But what we want is we want the battery to be cut off when we plug in a 5 volt, plug in the USB. So that should work here. And then either we have 8.4 volts or 5 volts coming in here, going through our fuse, ferrite bead, and this steps it down to 3.3 volts. And we need 3.3 volts because that's what our chip is running off. This is a linear regulator. There's two kind of ways that you can approach changing voltages and doing all this like power electronics. One is to use a linear regulator, and the other is to use a switching DC-DC converter. The switching ones are much more efficient. Essentially, you have a little chip that like turns on and off really quickly, feeds through current into a capacitor. Actually, I don't know how a buck converter works, but a boost converter, you're pushing in all of this current into a capacitor and it raises the voltage above what your input is. So that's how we step up from, for example, like 3.7 volts up to 5 volts. You can use a boost converter. Or here, in this case, we want to use a buck converter, which steps it down to 3.3 volts. And you can get efficiencies of like 96%, which means you're not really wasting any heat. Now, a linear regulator, it doesn't do any switching. So all of the conversion, all the power conversion is dissipated as heat. So that's what this does. And these generally get a lot hotter. You got to be really careful with how you do your thermals with linear regulators, but they're much easier. It's just like one chip here. Stepping down from 8.4 volts to 3.3 volts should be fine for the current that we're drawing. But it's something to keep in mind. Eventually, you want to switch to a buck converter, but they're much more complicated to generally deal with. And so the other thing I did from last week is I actually looked up how you hook up a SD card over SPI. So SPI is just one of the protocols that we use. And there's two sort of ways you can approach SD cards as well. You can either use the SDIO protocol, which is the standard for SD cards. Apparently, it's not like that protocol isn't very widely known or published in any way. So people have figured out how to use SPI to communicate with a micro SD card. And essentially, you hook things up like this. So your chip select goes to your chip detect here, mostly MISO and your clock signal. But you can just like look this up and figure it out. I'll just hook it up like this. Just copy me for now. Yeah, and 3.3 volts. This should be fine. So now we pretty much have everything hooked up. We have our STM32 here. And last week, what I was going to do was show you how to set all of like the pins up on this processor. And we downloaded this. So the STM32 Cube IDE. You can just Google that, STM32 Cube IDE. Click here. It's like 800 megabytes or something. I don't know. Just download whatever. Got the Windows one. Oh yeah, just click get software. You probably have to make an account, but we downloaded this and we didn't get around to it because it took too long to download, and I should have downloaded it prior to the workshop, but that's fine. So now it's totally downloaded, and so we can go through how to use this software. Oh, what's happening? So essentially, what this is a way to set up your processor. So tell it what pins should fulfill what functionality. You can say what kind of peripherals you want. So, you know, how we were talking about the protocols before, we can say, oh, I want I2C to operate off these 2 pins. And you can do, you know, configure your clock. So if you remember back here, this little oscillator circuit here, this is a high frequency clock at 16 megahertz. And we need that to make the chip operate at a higher frequency. It has like an internal clock. Basically, the clock is how a processor executes, how fast it executes its instructions. So, I mean, I'm sure on your like computer at home, some of the guys in here might know how fast their computers are clocked, but it's probably like gigahertz or something. But for us, for this tiny little chip, which is going to cost like $2 and have all this processing power, you know, 16 megahertz, we can use that 16 megahertz to go up to like 84 megahertz. And this is like a really sufficient sort of clock speed to do all kinds of things. But before we get into that, let's just have a look at the STM32Cube IDE. So when you open it, actually, I'm going to make a new project, and then we can just see what we get. Stock. Oh, actually, so the other thing that I remember last week, we had 2 STM32 chips sitting here. One was the STM32-405, and this one here, the 401. I was trying to decide which one to use. I did the 405 initially because I saw people using it online, and then I put in the 401 because it's a bit more like consumer grade. I think the 405 was kind of medical grade. It had like integrated CAN buses and all of this, you know, bells and whistles. It had some sort of like, what do you call it? Encryption on it. And that was overkill. So what we ended up, well, I ended up deciding is to use this STM32-401. And that's because there's a breakout board going around at the moment called the Black Pill. Oh God, what the hell? STM32. Here we go. Which you can actually use to test your programs before, you know, you actually buy a PCB and put the little chip on your own board. So here, this little thing here, that little chip is our processor. And what this board here is doing is essentially what we're going to be recreating as like one part of our PCB. So you've got your micro USB here, or USB Type-C actually. It's got a clock on there, an oscillator, which is that little, I wish I could like click on things. Where my mouse is, that thing. And then we have some like power circuitry and LEDs. So this kind of comes fully featured to hook up to a breadboard and then run all of your like sensors and peripherals off of that. The idea of PCB design is that we don't need a breadboard. So we have all of this on our chip, on our PCB, and all of our sensors on our PCB, and it's all integrated into one little solution. But I bought one of these on the weekend, and hopefully it'll arrive not too long, but it's bang good, so you never know. And yeah, we can actually start proving out the software and the configuration before, you know, you actually put it on a real board and get it ordered at JLC PCB. But anyway, the point is that this uses a STM32-401. which is, you know, pretty much good enough for us. It clocks up to like 84 megahertz. I was reading online, because kind of like the long-term plan for this kind of PCB, I want it to be spec'd to do thrust vector control sort of applications. So it's pretty popular online at the moment. You have a couple of servos that just point the direction of, I can probably show you. TVC mount. So basically this points the motor in different directions, and you can keep your rocket stable by, kind of like SpaceX, you know, it gimbals the motor and you can point it in different directions. And they say what you want for this is around like a 30 hertz control loop, you know, to run all your like PID control loop, do all of that kind of stuff. Write to flash. You can even like communicate over Bluetooth if you want that sort of thing. And yeah, you kind of want like 30 megahertz plus to do that kind of really fast control loop. And so the STM32 401, this can get clocked up to 84 megahertz. So it's a perfectly fine choice for us. Cool. All right. What are the alternatives to thrust rocket control, like airfoil things? I mean, you can have like active fins. Generally, like a normal rocket, you just design it so that it's stable, and so you have no active components, and it'll just fly straight. But you know, people work with active fins, which is a form of active stabilization. There's a lot of different ways you can do thrust vectoring, and then I guess like, yeah, other weird things. You can have like RCS thrusters, I guess, like little cold gas thrusters on the sides. Okay, so if we make a new project here. Oh, I also looked up another one recently called rollerons. If you want to look up what rollerons are for like intercontinental, like ballistic missiles, rollerons are a really cool invention. STM32, and we want the F401. Right, so basically just look up your part number here. We have a lot of different options. I think I just went with the RA here. So this is how you set up your project. Unit price $3. Awesome. And we want this LQFP64 footprint. That's kind of the package that it comes in. And that, you know, we can solder with that if we have to, if something goes wrong. So I think you click next, name your project, and it's going to download all of the files and the libraries that you need to work with this exact chip. So every single chip STM32 that you use is going to have a different library and backend, and so we'll have to download that for each different one. Yeah, and then you should, maybe I'll just do it. So let's do Aries Workshop test. And we can see what it looks like when it's just default. Now, the good thing about this is it has like like an actual GUI where you can pick what pin does what on the chip, and then it'll generate all of the code that configures the chip to do that. So for example, this is just your standard chip. Nothing is configured to do anything. All of these pins, it could be set to anything. So this can be an SPI, a GPIO, and then I think this one can be an I2C. So each pin has like a subset of all of the capabilities that the whole chip has, and you want to, I guess, like customize it for your application. And the way you do that is you first jump over to this connectivity tab, and it just has all of the peripherals that you can choose from. So you can say, all right, I want an I2C, and we just want I2C like that. And then you can see over these two pins became green, which means we can now use them for I2C. Now, once we save this, it will say, oh, do you want to generate code? Yes, please. And it will generate the functions in the main loop. So, oh yeah, by the way, this is all in C, but it's C with the hardware abstraction library from ST. It's kind of like another thing that you have to learn on top of this. But you can see here, now that we enabled I2C, it generated this function here, which has all of our I2C initialization code. And then for the processing that we want to do, like where you want to write your own code, it tells you, all right, we want to put our code within these blocks. Now we have to put them inside those blocks because when it generates the code, it'll overwrite anything that's outside of those blocks. So they're just like all around the place. Now, so for our flight computer, at the moment, I'll kind of go through what I'm thinking we want to use to set this all up. So we know we want an I2C line because that's going to talk to our two sensors. That's going to talk to our barometer and our IMU. Oops. We want an SPI line because our flash chip here, we talk to this over SPI, and then we also talk to our SD card over SPI. So let's enable that. And we want a full duplex master. So this just means that you can send and receive data at the same time. And yeah, in SPI, there's master devices and slave devices. It's kind of common for protocols to have that kind of architecture, but yeah, we want this to be a master. Now, we also want to enable UART. This is just very, very common protocol. A lot of people use it to connect to GPSs, for example. And we can just click asynchronous. So yeah, USART, this is the synchronous version of UART. But if we just choose it to be asynchronous, then it won't bother us because synchronous can make things a lot, can make things hard. Cool. And now to get a little bit fancy, don't worry too much, but this USB on the go, full speed, we want to enable this so that we can talk to the device over USB. So USB is its own protocol. And normally what you need on a board is to have what's called like a UART to USB bridge. It's a whole nother chip, which you can talk from the STM, from this chip here. You send out your UART signal, it'll talk to this external chip, and it will convert that to USB for you. And we need that because USB is a bit more complicated. It actually uses differential lines, which basically means there's two data lines. One is positive, one's negative, and it does some fancy stuff to make things faster and more robust. But what we can do is we can click here. We want, this basically emulates that within the chip. So we don't need an external USB to UART bridge. So if you click device only here, and then down to middleware, we're going to click USB device, and we want to create a virtual COM port. Cool. And that's pretty much it. So then your USB lines are going to connect to this data positive and data negative line. Cool. Okay. Let me just see how it compares to the other one. Oh, yep. Yep. Nope. Oh, the clock. Okay, that's cool. So yeah, every time you make a change, it's just going to generate the code for you. And so I think everything is the same, except for, obviously, when your chip arrives, the annoying thing is you can't program it for the first time over USB. We need to inject that code into it using an STM32 programmer. And if you remember, it's called an stdlink. This is what we were going to send out to winners of the competition later this year. Which we should actually, we might announce that soon. It'll just be like a little competition. Just design something very simple in KiCad, send it to us, and the winner will get one of these, and their design built by JLC PCB, and we'll like ship it to you. But anyway, so this here, this is how you program the ST for the first time. And so we need to set that up to enable that to happen on the chip. And the way you do that is you go to System Core. How did I do that? System. And then we want to set up the debug wire. And we want it to be serial wire, but we also want this trace asynchronous one. So you can see, if we turn this off, you can watch PA13, PA14, and then like PB3. When we turn serial wire on, these two come on. This is how you program it. So there's a clock line and a data line. This is how you program it for the very first time using the little dongle. But to make debugging easier, you want to click trace asynchronous, and that puts this pin on, which means that you can actually read, you can do like printf statements, if you're familiar with that. So within the code for this, you can just say printf and it'll spit it out over this to view actually within this software. So this is good for debugging. Now, the other thing that we want to set up is we don't want to use the internal clock. It's just not very stable or robust enough for our use. It's only advisable to use an external oscillator or clock with these things. So the way that you do that is you click System Core, RCC, and we want to enable the high-speed clock. We're going to use a crystal resonator, and that turns on these parts here. So this is where we're going to connect our clock input signal. Now, once you do that, you want to go into your clock configuration, and you can see that there's already problems. And it basically will solve the issue for you if you press yes. So don't freak out looking at this. This is essentially, you have your input clock here on the left. And then these are all the clocks that run all your different things, like your timers, your interrupts. Even here, there's like a 48 megahertz clock, which is for USB. And so I think this is something that we're going to have to play with in the future, but we're using a 16 megahertz external oscillator. So we're going to hit that there, and then we want to boost the clock up to even the max. Like, it might be a bit unstable at 84 megahertz, but it's rated for that, so it should be fine. If you just press yes, it's going to cycle through everything, try and find a solution that uses your input frequency, and it gives like a fair clock for every single thing that's going to be using it. So cool. All right, now we've set our clock to 84 megahertz, which is going to be like completely fine for anything that we want to do. It's going to be really fast and cheap. So we can hit save, and it will generate our code for us. And then we're pretty much done. That's the configuration for the chips that we're going to be using. And then it's onto the fun part of actually coding. But we're not going to code too much for a while. We're going to focus on this PCB for the moment. I'm just going to go to jlcpcb.com. So this is who we're going to have build our boards. You can see, look, PCB and SMT assembly from $2. Bloody crazy. And that's if you use their library of parts. So a good thing about their library is that they have a lot of STM32s. F401i, I think that's the one we want. Look at that, cool. So if we want, you know, you can see this thing is like 1 centimeter by 1 centimeter, little chip. It'll be kind of hard to solder this yourself with all these baby little pins. And so with their service, they'll do it for you. And so this is just going to come, and it's what, $3 for an 84 megahertz processor. Oh yeah, interesting. I don't know if you guys heard, but Nvidia bought holdings. Crazy. So we might see ARM chips get a little graphics boost. Some parallelization, maybe. I don't know. A CUDA core. Rightio. So let's get back to the schematic. And what I wanted to do today is generate the netlist and kind of like see the damage. So this isn't entirely done. One thing that I want to add is a UART connector here, or maybe an I2C connector. We probably should add both. So all right, you can follow along real quick. So all I'm doing is adding connectors so that if you want an external I2C device or an external serial device, you can just add them here. You can just connect it to the board, I mean. So here we've got our, I kind of want a 2x2. Oh, 2 rows, 2, 2. And so here I'm just going to put, oh, I might do it like that. I'm going to put all of our power. So what was this? This is going to be our I2C. SDA. You can, yeah, we actually haven't done any schematics for a while, but if you press A, that brings up your part library, and then W lets you draw wires, and you can just double click to end them. So what next? And then these are global net labels, which just means wherever you see that, instead of drawing a wire between SCL here and then SCL down here, it just assumes that there's a connection between the two. And then I'm just going to put our ground in 3.3 volts. Yeah. Let me breathe. If you hit M, you can move things as well. And then G, you can grab them. Whatever. No, let's do that. And then I want to copy that. How does one copy? Press C over it. And I want to connect here our UART, so our serial. And these are just going to be plugs that run off the board. UART RX. And our UART. Always remember when you're connecting your serial devices that the RX of one board goes to the TX of the other one. Don't make that mistake. Obviously, because when you transmit something, it should go to the receiver of the other one. Also, let me know if I'm breaking up. My My internet can be bad. I just got a notification saying internet bad. Okay. Cool. So, all right. Here's the frightening bit. So the first thing, if you remember, what we have to do after we have our schematic is we have to assign our footprints. Oh, and before we assign our footprints, we have to annotate it. So this just gives a little value to everything. Don't crash. And now we're here with all of our parts. So this is every single part on our schematic. And we have to give them all a footprint. So what they're physically going to look like on the PCB. Now, I think what I did, we have a ton more capacitors now. So we can go all the way down to oh yeah, capacitor SMD, surface mount capacitors. And if you remember, we're talking about sizes, like surface mount sizes. We're going to try to stick to 0805. It's kind of like a happy medium between something that's like so small that it's going to blow away if you blink, and things like that are too big and it kind of defeats the perfect purpose of SMD. I'm going to choose hand solder. Oh, and the picofarad ones, actually not sure. I'm just going to choose hand solder, but JLC PCB are going to solder it for us anyway. It's just if we want to take something off, may as well choose a bigger pad. Cool. Okay, so they're all of our capacitors because they have C's, and we're just going to make them all the same size. Our Schottky diode is just like a pretty standard. Oh, actually, no. Let's look it up. I think there's a diode called S3 something. Okay, no. So basically, I'm just going to look for what size the standard diode is. And we want a Schottky diode. Schottky diode. I've used this one before, I think. S34. Yep. And it doesn't give us a package. SMA DO214. Let's even see if that exists in KiCad. What was it? DO214. DO214 AC. DO214. It's probably just named something different. C80. Yeah, these should all be surface mount. Wait, other one. It's probably one of these standard sizes, to be honest. 214. Oh, Oh, SMA. Is that what you mean? Yeah. Oh, okay. Yeah, you're a genius. You are a smart man. All right, we'll chuck that in. Our fuse. Let's just choose like a 1206. So this is like a slightly bigger one. We don't want it to be the same size as the capacitors. I think fuses are normally a bit bigger, but we can always go back and change that. Ferrite bead. Sometimes they're under inductor, SMD. Let's just look at what options there are. Ferrite bead. Oh. Yeah, they're basically these. And I mean, they're going to be 0805 anyway. Connector, odd, even. All right, let's just choose. So for connectors, there's a lot of different options. You can have like terminal blocks or like female headers. I think we want, always choose 2.54. They're nice. And we'll just want, so J1, J3, yeah. A 2x2. So vertical SMD, vertical through hole. Yep. No chrome wire, let's not worry about that. STM32 programmer was 4x2, I think. This is another header here. Okay, so 1, 2, 3, 4, 5x2 header. 2x5. Yeah, let's not pick surface mount. This is also another 2x2. 2S battery, let's not worry. SC cards, I don't even know if they have a footprint for that. Let's not worry about that. Micro USB. So normally you want to put a lot more thought into this. We're just going to do it quickly so we can get on the PCB today. Where's my USB? There. And I want type B because they're nice and easy to work with. Micro B, mini B. So what I'm thinking about when assigning these, or at least when I'm assigning the connectors, I'm thinking about, actually there's not too much thought. You kind of just want to ensure that for the connectors, it's something that you're going to easily be able to use, either like surface mount or through hole. I recommend through hole just because you're going to solder it yourself, and surface mount connectors can break off a lot easier. Through holes are a bit stronger. But right now I'm looking at all of these USB footprints and I think we just like go ahead and pick one for now, but not a vertical one. We want a horizontal one. And now all of these resistors here, let's just go back and make them all 0805. When you're looking at resistors and their sizes, generally the larger the size of the resistor, the more power it's going to be able to dissipate. And so you really want to make sure that the resistor that you're picking has the thermal, it can dissipate the heat that it's going to be running, right? So basically you have your voltage across a resistor, a certain amount of current going through it, and power equals voltage times current. And so that's going to give you a wattage, how much energy it needs to dissipate per second. And for some tiny resistors, like, what am I looking at here? 0805. For some tiny resistors, you can get like ones that only dissipate 1/16 of a watt or something similar like that. Let's not put the clock in for the moment. Yeah, so you can get like 1/16 watt resistors. And so if you're going to be putting too much power across that, it's going to either melt or explode or pop off the board and you'll have a problem. It could even short. So that's actually interesting thought that when you have failures on a PCB, there's no guarantee that it's going to fail as an open or a closed circuit. So for example, a transistor, I might assume, so if this dies, it might cut itself open, right? And so now you have, the battery will just be disconnected and nothing is going to be able to move through this transistor. But at the same time, it could fail as a short, which means now this battery is always going to be connected. You have no protection. If you connect a 5-volt USB, you're gonna blow something up. All right, now we want to generate a netlist. Save that. And for the first time in a couple of weeks, we can go over to our actual schematic here and put all our parts on. So we'll click our netlist here. And so we did this the other way. You just, I'll go through it again. But you define your edge cut. So this yellow line is telling the program where the outside of the board is. And then this big green layer here. Oh, okay, there we go. This big green layer is a big copper port, which all of this here, all of it is considered ground, so you can connect things up easily. Now I have a bunch of errors here because I didn't give footprints for everything. So it's angry at me, but it should still work. It did, for better or worse. Cool. All right, so here are all our parts. And it remembered how we arranged our BNO. So this is our accelerometer, our gyroscope, and our magnetometer. So we did that the other week. Now we have the joy of all of these parts here. We're going to have to find a spot for them on the board. Obviously, we can make the board bigger. We have complete control over that sort of thing. But the issue is going to be running traces between all of these components. So how about a good way to start is let's just go through and identify everything first. Yeah, identify everything first. And then we can get a good feel for what, PCB design is. So this here, yeah, this is our USB. So I picked a weird footprint for that. It's a through hole one. I'd rather surface mount, but let's just see if I can change that. So to change something, you want to go in here, find the offending part. And then we want to try something different. I think there's going to be a way to preview these. I haven't come across that yet. I haven't even given it a go yet, so maybe let's try. Found it. So all of these are through hole, USB 3A. I like Molex. So if there are any, there's a type C Molex. Micro, micro obviously. Yeah, that's what we want. Don't know what micro AB means though. Micro USB. Okay, that looks more like it. Cool. And now we can just double click and that changed our, can't it go away? Okay. And then we generate a netlist. I think I did it. I think that did it. And let's import it. Generate netlist. Yeah, let's save that. All right. It might be angry because there's a lot of errors, obviously. And maybe we can just hit delete on that. Did it put it in there? No. Maybe, no. All right, let's try one more time, but if this doesn't work. Oh, there it is. Okay, yeah. So we already had a component named J7 on the board, and so it didn't want to import another one for it. But cool, all right. So here, now we have our USB. So let's just chuck that somewhere. I'm going to hit Alt-3 to view this in 3D. And so we can see all of our parts that we have to put on. Cool. All right. Oh, obviously chose a wrong. So this big transistor here is not the package that we want. We want everything surface mount. So the task is to put all of this on their respective spots on the board, figure out the placement, figure out nice placement so that everything kind of works together and they're easy to route. And so PCB design kind of gets to a point where it's very, it's more of an art form than anything structured. And a lot of the way that you do these things comes from experience. So like placement, oh, where do I put this board here, which is our barometer, I believe. You can put it anywhere, but you see a lot of these rat nests, so the rat nests are the little lines, run over to this bad boy, and this is our STM32. So obviously it's going to be connecting to everything. So challenge, how do we connect everything? It's a bit of a slog. It takes a while, but when you slowly start to put everything together, it will start to make sense. It's just about practice, really. Put things in different spots, start hooking them up, realize, oh, that's not going to work. How can I do it differently? Try again. So for example, I kind of just move it around and see, all right, so all of these connections actually want to connect on this side. You can press R to rotate things. Oh, actually, so this is our SPI chip. Now, what you can do is hold Shift X. That brings up our routing tool. And so just as an example, we're going to connect this chip select. Click that, and then we can draw out our trace. And there we go. That's one connection. I think it says, yeah, actually, unrouted traces 111. And so this kind of thing, chances are, oh, where's this even connect? Chances are it might not even work at the end of the day. You start doing things and then you realize that components aren't, they physically can't be connected. And then you have to redo everything. You might have to start from scratch. For Swoop Aero, I was close to finishing. And then I realized a lot of the components weren't even available anymore. And so I started to wipe it clean and start again. All new chips, all new components. But the thing is, once you do it once, it starts to get faster. So here's another thing, if you don't remember. If we start routing something and press V, we place a VR. And a via connects the top layer to the bottom layer. So this ground, we just want to connect ground to this big green section on the bottom of the board. We're coming to the end of time, but you can see how you can start to build up a full design. So I'll start with the big components. Just place them around, see kind of, it's a weird diode, like really big pads. Just like see where they're kind of fitting, see where everything connects like in a higher sense. So like put components that are similar or components that are meant to be together as well. For example, for our IMU here, we put all of the resistors and capacitors around it that we know we're going to need. And do that for every single chip first. And then group similar components. And then start routing between them. It could take ages, you know. It could take ages, or you might get it right on the first go. You never really know. Where's our linear regulator? So yeah, I'll probably start from power and then just go all the way through. So USB, then we come to our power chips, go to our STM32. We know that's going to be talking to our flash chip here, IMU here, barometer here, and then we have our plugs here for off-board things. What are you? Cool. So that was a bit of a crash course in all of this again. I think maybe next week I'll have to think about how to route this. I'll choose all of the right footprints, and then I'll just go about routing it. I won't do too much before then, just so we can actually go through the process of how we route these kind of things. Yeah, I think that'll be the plan. I won't touch it too much. I just neaten everything up. But if you guys do want to like catch up, look at the YouTube videos. Just copy everything, totally fine. Do your own research. If you find something, come to me and tell me like, oh, this is a better way to do it. Let's kind of try to build this together.